All right, there we go. Now we're recording. Oh, whoops. Can't get out of there when I do that. There we go. Okay, so we are on to 4.3, the first derivative test. This is chapter 4.3. And again, what we're doing here is we're using the first derivative to tell us when we have a local maximum and a local minimum. The first derivative test tells us that if c is a critical number on a continuous function f, if f primed of x, if the derivative changes from positive to negative at c, then f has a local maximum at c. If the derivative changes from negative to positive at point c, negative to positive, then it'd be a local minimum. So positive to negative is a maximum, negative to positive is a minimum, and if it does not change sign, then it has no maximum or minimum at point C. And here's a nice little diagram that I just stole from an old textbook that really, I think, illustrates this well. Let me make that a bit bigger. So we're going to do those interval charts again. And if we find out that if we're left of point C and right of point C, if we go from positive to negative, that means this is what's happened. That means that the tangent used to be sloped up and now it's sloped down, so that point C must have been a local maximum. If we go from a negative slope to a positive slope, we must have had a minimum. If there was no change in the direction of the slope, then point C, again, here's the instantaneous place where the tangent was 0, but that doesn't mean that that place was a maximum or a minimum. And of course, if they're both negative, it's just a change in direction, but the other way. And those two tangents don't mean, because they're in the same direction, that means that this point is not a maximum or a minimum. Okay, so we're going to do an example here different than the last few we've done. We're going to, instead of starting with a graph and then filling in the parts we don't know, we're going to just completely not even start with a graph. We're just going to start with the algebra here. Okay, so find the local maximum and local minimum values of that equation. Okay, so we're going to start by doing the derivative. So f primed of x is 3x squared minus 3, and that's it, right? Derivative of 1 is 0. And of course, we're going to set that to 0. And then we're going to, we'll factor out a 3, divide both sides of the equation by 3. And then the derivative is 0 when x, this of course is a difference of squares. So my derivative is 0 when x is negative 1 and positive 1. So those are my critical values. Might as well make points out of them too while I'm at it. So what is f of 1? Well, let's see, f of 1, if I run through there, that'd be 1 minus 3 plus 1. So that'd be 1, negative 1. So that means I have the point 1 comma negative 1. That's one critical point on this graph. And the other one happens when I have x is negative 1. So that'd be negative 1 cubed is negative 1 plus 3. So that's negative 2 plus 1. No, hang on a second. Do I have that right? F of negative 1 is negative 1 plus 3 plus 1. So that one's just going to be 3, right? Right. Negative 1, 3. And there we have it. So there's the two, what we call critical points. Now, I don't know anything about the shape of this graph, right? Are those points maximums, minimums, or is it just a point where the graph changes direction? Because remember, x cubes have those kind of points, right? X cubed, just your basic x cubed graph, you don't have to write this down, but you should know this, does this, right? It just changes direction. At this point right here, I would get a critical value, but that's clearly not a maximum or a minimum. So what's the situation here? Are those maximums, are those minimums, or neither? So the way I'm going to figure that out is, again, to set up one of those interval diagrams or interval charts, whatever you want to call them. So my intervals are, okay, so what happens? So the C points are negative 1 and 1. So what happens when x's go to the left? left of -1, that's one interval. Then I have an interval between -1 and the next one, which is 1. And then I have an interval after 1. So those are my intervals, right? What is this graph doing on either side and between those critical values? Okay, now what's the equation? Well, the equation is 3x squared minus 3, but the part that matters, the part that tells us whether we're going up or down, really, I'm going to use this factor part. So I'm going to use the two factors, x plus 1 and x minus 1. Then I'm going to tell you if f primed overall is going positive or negative, and then I interpret that. I think the book doesn't put an extra line on here, or an extra part to this chart, but I like having this part where I just determine whether I'm increasing or decreasing. So here we go. So x plus 1. Pick a number smaller than -1. Well, -2 sounds reasonable, right? So let's pick -2. -2 would make this factor negative. It would make this factor negative. And a negative times a negative is a positive. So it's increasing on the left of my first critical point. What's happening between the two critical points? Well, I think the easiest number to work with between -1 and 1 would be 0. So 0 makes this a positive, makes that a negative. A positive times a negative is a negative. So we are decreasing between the two critical points. And then after the last critical point, as I go to the right, a number bigger than 1, 2 makes sense. That makes that a positive, makes that a positive, and I get a positive. So we're increasing again. Okay, so let's interpret what this just told us. Let's make a conclusion based on this chart. Therefore, x equals -1 is a what? It has to be a local maximum. How do I know that? Because I'm increasing to the left of it, and I'm decreasing to the right of it. So it must be a local maximum. X equals +1. Okay, look at what's happening. On the left of -1, it's decreasing, and then to the right of 1, it's increasing. So it must be a local minimum. So now, even though I don't know anything about the x-intercepts of this graph, I can give you a reasonably good sketch of what this graph must look like. I mean, what do I know about this graph? Let's go back to the original equation. You could try to find the x-intercepts using the factor theorem, right? Remember the factor theorem says if there are whole number or integer factors, then those integers must be factors of 1. And, well, that's 1 and -1. Does 1 make this a 0? No. Does -1 make this a 0? No. So I don't really know. I'm going to have some sort of at least rational numbers for my x-intercepts, and possibly even irrational numbers. So I don't know much about that. I guess I do know a y-intercept, right? My y-intercept is 1. So now I know I know a local max and a local min and a y-intercept. So I could make a sketch of this thing, right? I know that we have a point here, again, a y-intercept of 1. And then I know I have a critical point at, what was it? -1, 3. So -1, 1, 2, 3. So there we go. -1, 3, right? And then I also have my local minimum at 1, -1. I also know that any x cubed that has a positive coefficient in front of it goes down forever on the left and up forever on the right. Right? All odd exponent degrees have one arm going one way, one arm going the other way. And from left to right, it goes from negative to positive because this is a positive. And again, you learned that in grade 12. So I do know that this thing does have to go back down this way. But it goes like that. Oh, I'm supposed to, oh man, I missed the dot there. Let's try that again. And there we go. So even though I don't really know what these numbers here are, I can still get a pretty accurate graph. And as always, this is always the fun part. Like, graph it on Desmos and see how close we got. Let's see. Oop, that's not what I wanted to do. Let's see. I haven't opened Desmos yet today. Let's get a Desmos happening. And let's see. I think I already have this thing graphed someplace. Come on, Desmos. Uh-oh. There we go. And, oh, good, I'm logged in. And there we go, 4.2 graphs. And there it is. Oop, that's not what I wanted. There we go. There, that's pretty close to the sketch I just made, right? And I was right. This X-intercept here is not a whole number. Neither is that one. Neither is that one. Actually, now that I know the critical values and I know the direction the arms have to go, I actually know how many X-intercepts there are. I didn't even know that before the critical values, right? Because it is entirely possible. Let me go back to the sketch. It is entirely possible that there's such a thing as, a cubic that only has one X-intercept, right? But this one has 3. 3 is the most it could have, right? All right, let's do one more example like this, where again, I don't know anything about it going in. I don't know that my X, oh, let's see, could the X, again, if there are integer X-intercepts, they have to be integers that are factors of -1. So that's just plus or minus 1. Does G of 1 equal 0? That would be 1 minus 4 minus 8 minus 1. Nope, not even close. Does G of -1 equal 0? That would be 1 plus 4 minus 8 plus, nope, sorry, I just did that wrong. Minus 1. No, it's not. So once again, my grade 12 skills fail me. I don't know anything really about this curve. Well, once again, I know the y-intercept. That's nice. I know the y-intercept's -1. And I know that both arms are going up eventually, because it's an even power for my highest degree. And that's it. That's all that my grade 12 skills tell me. How many X-intercepts does it have? Could have 4. Could have 0. I don't know. Okay? So I need to use critical values. So let's find the critical values. G primed of x is, that'd be 4x cubed minus 12x squared minus 16x plus 0. Okay, with me so far? All right. Critical values happen when I set this derivative to 0. So setting this to 0 and making a mistake. Oops. Setting this to 0. All right, what would I do with this mess? Yep. Factor out of 4. Or actually, maybe better, divide both sides of the equation by 4. Just get it out of the way. That I will factor. Okay, so I'm going to divide both sides of the equation and factor out of 4. I'll do both at the same time, just to see if I can mess it up by doing too many steps at once. So 16 divided by 4 is 4, so that's minus 4. There we go. Okay. Don't divide both sides of the equation by x, because then you'd lose one of your critical points, because one of them is x equals 0. And again, those of you who've gone through the grade 12, remember they always warned you about that when you were solving trig equations. Don't divide both sides of the equation by sine of x, then you lose the answer sine of x equals 0. All right, now this thing, I believe, factors, right? X squared minus 3x minus 4 equals 0 does factor. If it didn't factor, I'd break out the quadratic formula. All right, but it does. So this is x minus 4 and plus 1. So there's my other critical value. X is 4, or values, -1. Okay, so those are my critical values. Let's find the critical points now. So my critical, those are values, but to turn them into points, I need their y-coordinates. So go back to the original equation. And, okay, I've already kind of calculated this. When x is 0, you get -1, which we kind of knew already. That was the y-intercept. Turns out the y-intercept is a critical point on this one. And let's see. What happens when x is 4? I already ran 4 through here the other day when I was getting this ready, and I end up with a -129. And my other one is -1 for x, and when you plug -1 and run it through there, you get -4. So there's my critical points. Okay? Are those points maximums, minimums, or neither? Let's find out with a chart. So, I like making my chart like this. Interval. And okay, let's see, what are my intervals? Which one's furthest left? -1's the furthest left. So what happens to the left of -1? Then the next interval is between -1 and the next one's 0. Then the next interval will be between 0 and 4. And then one last interval, what happens to the right of 4. And there we go. There's my intervals. I have 1, 2, 3, 4 intervals and 3 different factors to worry about. I have the x factor, I have the x minus 4 factor, I have the x plus 1 factor. Then I want to know what the function's reciprocal is doing, and then I want to determine if that's an increase or a decrease. Okay? All right. What did... -2 sounds like the easiest number to work with that's smaller than -1. So that makes that a negative. That makes that a negative. That makes that a negative. A negative times a negative times a negative is negative. So we're decreasing when we're left of -1. Okay, this is a little harder. Between -1 and 0, I don't have any whole numbers, so I'll have to use maybe -1/2. -1/2 makes x negative. It makes x minus 4 negative. It makes this positive, right? Because a half is not going to cancel away 1. So a negative times a positive is positive. So we're increasing on this interval. Between 0 and 4, you have 3 integers to choose from. I'll pick the smallest one. I'll pick 1. 1 makes that a positive, makes that a negative, makes that a positive. A positive times a positive is negative. So we're decreasing. And x is bigger than 4. I'll pick 5. Positive, 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 positive. So we're increasing. Any questions on how my thinking is working here? Okay. All right, now what can I conclude from this? It's one thing to be able to make the chart. You got to understand what the chart's telling you. What's this chart telling me? This chart's telling me that therefore I have a local maximum. Where? Where is there a local maximum? If it's decreasing on the left and increasing on the right, that's a minimum. So it has to be increasing on the left and decreasing on the right. So it's that one, yep, 0. So my local maximum is 0. What was the x? Oh yeah, 0, -1, right? Yep. 0, -1 is the local maximum. Okay, now local mins, I think I have a couple. My local minimums. It was decreasing to the left and increasing to the right of -1. And what was -1's y value again? -4. And it was decreasing to the left and increasing to the right of 4. And that was 129, wasn't it? Am I right about that? 420? -129, which makes sense. It's way down there. It's a minimum. Thank you. Okay, so let's make a sketch. What do we know? This is going to be very not to scale. Or more accurately, I'm going to make just a normal 1, 2, 3, 4 scale this way. But I'm going to count in much bigger numbers up and down. So 0, -1 is like going to be really close here, because I got to count all the way down to 129, so it's going to be like really close like that. So 129 is like way down there somewhere. And then this is -1, so you're not going to tell much of a difference between those, but that's still definitely a local minimum. So I know both arms go up, so I know that I peak down there, peak up there, and then I go way down to 4, -129. So I don't know, maybe like way down here. And if you're wondering, well, how can you tell what the scale is? Well, I can't really. I know the arm goes back up again somewhere. So I know it's going to look something like that. And it's actually helpful to maybe put the actual labels on there. So this was -1, -1. This was 0, -1. This was 4, -129. Oh, was it -1, -1? Oh, it was -1, -4. Sorry. Right. So it's going to be something like that. Just to prove that that is what's going on, let's take a look at Desmos. Desmos. Come on. Come on. Something's What's wrong with, oh, come on, my big stubby fingers. And let's see, let's close that one, and there it is. It's something like that. And yep, as you can see, let me shrink that. Actually, maybe it'd be easier to just take this and change the y-axis to put some numbers like, say, -10. Oh, wait a minute, it's the y-axis. Yeah. We want to go to where's my negative button? -135 or something. And let's go up to, I don't know, 20 is fine. And then for the x-axis, we only need to go from, say, -5 to 10, maybe. There we go. There. Oh, did I not go far enough? What? Did I not type that in right? I must have missed it. Hang on. 130. There we go. Oh, for some reason it's messing me up. Oh, -1. Oh, I put the wrong side. Sorry. -130. There we go. There. Something like that. That's pretty close to the sketch I had, isn't it? Okay. Again, I don't really know what these X-intercepts are. I'd use a graphing software if I had to find them. In the old days before graphing software, you used to Goldilocks them, right? You'd use your critical values to tell you, well, I know it must hit the x-axis somewhere around here, and then you just make a table of values where you try numbers on the left and right until you got close to within 0.5. It was quite tedious. So there we go. We'll do a couple more examples like this from 4.2 tomorrow. Okay, music guys, we'll let you go a couple minutes early if you got to run to music, since today's your first day back at music. Okay, that's all for the actual lesson today. I'll shut down my lesson. Shut down the video. If there's people who want to stick around and have implicit differentiation questions to get ready for Wednesday's quiz, I can answer those. Okay, stopping the recording.